Lesson 37 activity. Today the activity comes before the demo, so watch this video before you watch the demo video. In this class we calculate distance traveled given a velocity curve. We'll start with the group activities today and do the demo in the last 15 minutes of class. Our old zombie friends Feynman, Hertz, and Author and Planck decide they're dying to run another race. After all, they have lots of time on their shriveled hands. This time the graphs below give each zombie's velocity in miles per hour as a function of time in hours. So, for example, over here on Hertz's graph, the vertical axis, well, on all the graphs, the vertical axis is velocity in miles per hour, and the horizontal is time in hours. Okay, so number one, describe each zombie's race. So we're just looking for English descriptions for how these folks raced. So Feynman's velocity was constantly 1, and that means that he was limping along at a constant speed of 1 mile per hour, no deviation in his speed. Hertz's velocity was lower in the beginning, maybe around a half, and then ended up higher, maybe around 1.5, and he was constantly going faster and faster and faster. So he started slow and then sped up at a constant rate, moving faster and faster throughout the race. Noether's strategy was exactly the opposite. She started off going 1.5 miles an hour and slowed down constantly until she was just barely hobbling along at the finish line at 1/2 mile per hour. So she started fast and then went slower. Planck had the most complicated strategy. He started at a dead sprint of 3 miles per hour, but then that was way too much to keep up. So he slowed his pace down rapidly, slowing down, until right here, where for one brief moment in time, his velocity was exactly 0. He stopped for a little break to nibble on some brains, get his energy back up, and then slowly started to walk and then jog and then sprint until the finish line, running hard 3 miles an hour right through the finish. So I'm not going to write the answers down. Well, I guess I will. I'll pause the video and write the answers down. Okay, let's take a look at 2. What distance did Feynman stagger? How can you tell? Okay, let's take a look at his graph. All right, so Feynman's graph is the easiest to analyze because Feynman ran at a constant rate of 1 mile per hour for the whole race. And so we know that the distance traveled is rate times time. And the rate was constantly 1 mile per hour and the time was 5 hours. And so altogether he staggered a total of 5 miles. And the reason we can use that D equals RT formula is because the rate was constant. Okay, on the next page, what distance did Hertz limp? How can you tell? Okay, so Hertz's graph is this top right here. This one would be challenging, right? Because at every moment in time, his velocity is different than it was the previous moment. However, if we're clever, we can say, well, the velocity here, maybe it was 1/2, and the velocity at the end is maybe 1.5, but they average out to 1, right? And so we can pretend that at this one instant and at that one instant, he was actually moving at 1 mile an hour, the average at both of them. And then if you pick like this point right here, it's got a corresponding partner over here. And again, they both average out to 1. And so just because this is a straight line, we can actually pretend that he was traveling 1 mile an hour constantly. And so it's actually the same answer as to the question for Feynman, because we're kind of clever about using the linearity of that one. So Hertz, we can do the same distance equals rate times time. And so it's still 1 times 5 or 5 miles. And this is because Hertz's, is that how we do that? Apostrophe S. Average speed was 1 mile per hour. Okay, but now we're going to answer that same question in a different way, a way that's a more calculus way, and a way that's going to go somewhere good. So we're going to determine a low estimate for the distance Hertz ran by assuming that he ran 1/2 mile an hour for the first hour. Let's take a look at his graph right here. So here's the diagonal line. That's Hertz's actual graph. But we're going to make simplifying assumptions. We're going to assume that in the first hour, he was running at this constant speed, which is around 1/2 mile an hour. And then in the second hour, he was running at this constant speed. which is around 0.7 miles an hour. And so in each hour period, we're just going to look at how fast he was hobbling at the start of the hour, and we're just going to pretend that instead of accelerating constantly during the hour, he just kept his velocity the same during the hour. He kept it at whatever his starting velocity was at the beginning of each hour. So 0.7, 0.9, whatever this one is, 1.1 maybe, and 1.3, okay? And so we're going to make these assumptions because if we assume that he is traveling constant velocities for each of these hours, then we can use our old friend distance equals rate times time. So this is an alternative to what we did up above. We actually just got lucky up above because we were able to average out his velocity, but we won't be able to get lucky in that way for the parabola looking thing in the bottom right of the previous page. Okay, so in this case, this would be a low estimate because clearly we are underestimating his velocities at every moment in time, except for the start of each hour. We're getting it right just at the start of each hour, but then we're underestimating for the rest of the hour. So the distance is equal to rate times time, or velocity times time. So the velocity in the first hour we're assuming is a constant 0.5 times 1 hour, plus, that's just the distance for the first hour, but now in the second hour, it's 0.7 miles an hour times 1 hour. Third hour, 0.9 miles an hour times 1 hour, plus 1.1 times 1 plus 1.3 times 1. Okay, and so we smush all these things together, 2, 3.2, 4.5. 4.5 miles is our underestimate. Clearly, it's an underestimate, and yeah, I mean, we knew the right answer is going to be 5 miles, but this is a good start. 4.5 miles for an underestimate. Okay, similarly, we can come down here and determine a high estimate, an overestimate. And so in this picture, how about we look at the velocity in that first hour, and instead of picking the velocity from the very first moment in that hour, we instead pick the velocity at the last moment in the hour and assume that he was traveling at that last velocity for the entire hour. And so this is going to overestimate what he did in the first hour. We're going to assume that his velocity in that first hour was constantly 0.7, even though he only got up to a speed of 0.7 at the very end of that hour, and he was traveling slower than 0.7 miles an hour for the rest of that first hour. But let's assume it's a 0.7 for that. And then at the end of the second hour was 0.9, and we'll just assume that's constant for the whole second hour, and then 1.1, 1.3, and about 1.5 there. So this will be an overestimate in the first hour, 0.7 miles an hour times 1 hour, 0.9 times 1, okay, so let's do this calculation. 1.6, no, let's do it differently. 2, 4, 5.5. So this is an overestimate for sure, because at every moment in time we assumed he was traveling faster than he actually was, except for the last moment of each hour where we hit it exactly. And so really the right answer is something in between our underestimate of 4.5 and our overestimate of 5.5. Again, we knew the right answer was 5, but okay, so you can do the same thing for number 5 here for Nother. This is Nother's graph copied twice. Even if you already know what the answers are, go ahead and draw horizontal lines in the graphs below and do the calculations from scratch. Pause the video here if you haven't had a chance yet to do this. Okay, so then for the first one, if we're doing a low estimate, in the first hour, her lowest speed was at the far right. And let's draw a horizontal line right there. And in the second hour, the lowest speed was at the far right. And in the third hour at the far right. So all of these are underestimates. Of course, it's going to be the same calculation. It's the same 4.5 miles that we got for Hertz right up above, but it's important to be able to draw these lines. And the second graph is supposed to be the one where we overestimate the distance. So draw those lines in. In the first hour, we can assume a constant speed of whatever she was doing at the start of the hour, maybe 1.5, and then overestimate in the second hour, third, fourth, and fifth. And so probably good for practice to just write out the calculations, but of course we know what the answers are going to be, right? The underestimate here is going to be 4.5 miles. And then the overestimate here is going to be 5.5 miles. Okay, number 6 is now for plank. And so what we're going to do is instead of going 1 hour long segments, we're going to do half an hour long segments. And so we're going to pick a low estimate and a high estimate. Let's do the low estimate first. First thing I'm going to do actually is cut my 0 to 5 up into half-hour segments. So 0 and a half and 1 and 1.5, etc., all the way to the end. Okay, and so let's do the low estimate first. So for the low estimate, in the first half hour, we are going to pick the slowest speed that he was shambling, just between 0 and a half. So the 2 points that I have to pick, I guess I pick any point I want, but in the first half hour, it looks like maybe here and here. And so of all of these points, we're going to pick the lowest speed that he was traveling and assume that that was the speed he was traveling for that first half hour. The lowest speed I see is right here, and so our line is going to be this one. So let me get rid of all this stuff and just draw in my green underestimate. Actually, let's do it in orange. So here is my first half hour. We're assuming the speed was constantly 2. And then in the second half hour, so let's go right here. So the choices are, let's see, it looks like the end of the hour is there, the start of the hour is there, and I've got all of these possible velocities in between. And for this part of the problem, we're doing a low estimate, so we're always picking the slowest speed in the half hour, and that's going to be right here at the bottom. Let's get rid of that and just draw the one line that we want, which is here. Okay, so pause the video here and then go ahead and draw in the rest of these low estimates and then come back. Okay, so I've drawn a couple of the low estimates here, but I just want to point out this little detail here. If we're looking between 2 and 2.5 hours, the slowest speed in that half hour is actually 0. So we're going to assume that he was moving 0 miles per hour for that whole half hour period for our underestimate. And then things change. Between 2.5 and 3 hours, the lowest speed is actually at the left, and we're drawing to the right. And then between 3 and 3.5, the lowest speed is right here. And so we're not consistently drawing from the right to the left. We're just picking the lowest point in each half hour. Okay, so we've got 10 orange line segments drawn in here, representing 10 constant velocities over 10 half-hour intervals. And so then we'll do our calculation for the distance traveled. So in the first half hour, remember it's rate times time. So the first half hour is 2 miles an hour times the time, which is half an hour. It was only in the previous couple of problems where it was always times 1, but that is not the norm. Rate times time, plus. So that is just the estimate for how far he traveled in the first half hour, but now we'll do the second half hour. Looks like maybe 1.1. That's the rate times the time, another half hour. Plus third half hour. So I'm looking right here and I'm trying to estimate the y coordinate, maybe 0.5. And again, that is times half of an hour. Plus, and then we keep going. In the next half hour, maybe I think 0.1, 0.2, either one is probably okay with me. I'll call it 0.2 times half an hour. And then the fifth half hour, velocity we're assuming is 0 for half an hour. Plus, and then in the sixth half hour, again, it's a 0 times half an hour. And in the seventh half hour, 0.2, and then 0.5, 1.1, and 2. Okay, so crunching all these numbers together, what do we have here? 2, 3.1, 3.6, 3.8. Is that right? Let's hope it's right. think that's 3.8, adding them all up. Okay, feel good about that. And then the next question, next part of the same question involves doing high estimates, over estimates for each one of these intervals. So we're going to do the same thing, but pick the highest point on every half-hour period. Okay, I just looked at the answer key in the activity here. It has 3.6 miles, so it just means that we pick slightly different numbers, but that's okay. It's all estimates here. So this is another one of these problems where there's a range of acceptable full credit answers. Okay, so let's go in the first half hour here. The first half hour starts there and ends there. We've got this whole range of green velocities, and now we're trying to overestimate how fast he ran. So we pick the fastest point in that half hour, which is up at the top, and we go to the right. So let's get rid of that and just draw the one green line, which overestimates. And then in the next half hour, that's here to here. The choices are from here to here, and you're picking an overestimate, so that's up at the top. Now, some of you might recognize that we're going to be doing a lot of the same calculations as we did before, a lot of the same numbers. Still, I think it's a good idea, even if you can see some shortcuts here, just for practice, because this is our first one. Go ahead and draw all the lines and write out the calculations just like we did over there. So in the next half hour, it's here. In the next half hour, it's here. And the next half hour, it's here. And now things change. When I look at this half hour between 2.5 and 3, I'm trying to pick the highest point in that interval, and that is here, and then going that way. So all of a sudden, the way that I draw these lines is reversed. So now it's this one going this, and then the highest one on each interval is going to be on the right, at the right endpoint. So we should still have 10 numbers we're adding up, but these ones are all overestimating the distance traveled. The first half hour, let's call it 3. That's the velocity. So velocity times time, half an hour, plus. In the next interval, we called it 2 before, so I guess we should still call it 2. Plus, and then we called it 1.1, and then we called it 0.5, and then we called it whoa. Each one times half an hour. And then, so that's the first 1, 2, 3, 4. And then 0.2, so that's our fifth one. And then our sixth one is exactly the same as the fifth one. So that was the 0.2, and now we're doing this next 0.2 right here. And then they just reverse. Okay, so I think this is just going to be 6.8. Really hoping that I got that right. And I can't check the key because it's just going to have a different number from me anyway. All right, I feel good about 6.8. And so again, probably the true answer, not probably, for sure, the true distance traveled is something between 3.8 and 6.8. So our best guess, I guess, would be the average of those two, but there's no way to guarantee it's always just going to be the average of those two. In fact, it's almost certainly not the average of those two. Number 7, how did the estimates for distance each zombie ran relate to the area between their velocity curve and the x-axis? Well, let's take a look. Let's look at the I don't know, let's do the green areas that we just calculated. So take a look at this rectangle right here. If we wanted to calculate the, I said we were going to look at green. Let's not look at green, let's look at orange. Take a look at this rectangle right here. If we were going to calculate the area of that rectangle, we would do the height times the base. The height is 2, pretending it goes all the way to the top there. I just sort of missed. I didn't want to draw over the orange. So the height is 2 and the base is 1/2. And so the area of that rectangle is 2 times 1/2, which lo and behold is exactly the calculation we did for the distance. And then the next rectangle would be this one here. I'm going to draw like there's a space, but there's no space in between these two rectangles. And so the area of that rectangle is the height, about 1.1, times the base, which is 1/2. And so 1.1 times a half, again, is the calculation we did before. We did it in the context of distance traveled over that period of time, but it's actually, maybe surprisingly, the same as the area of the rectangle. Distance traveled is the area of the rectangle. Okay, but that was for the rectangles, and we're trying to think about the area under the curve, between the curve and the x-axis. So would you agree that the area of this rectangle is doing an okay job, not a great job, but doing an okay job of approximating the area of this curvy shape right here? It's straight, straight, straight until the end, and then it's going to follow that curve. So clearly the area of that purple rectangle is less than the area inside of that blue shape. But what we really want to do, if we're being exact, is actually calculate the area of that blue shape. We used 10 rectangles here. If we used 20, then we would be cutting this blue shape, and we'd be finding a rectangle that approximates the left-hand side of the blue shape, and then maybe another rectangle that approximates the right-hand side of the blue shape. And those rectangles, those two rectangles, would do a better job approximating the area of the blue shape than our single rectangle does. Let's see if we can answer the question. So this is kind of a preview of what we're doing in the coming classes, but how do these estimates relate to the area between their velocity curve and the x-axis? So the area between the velocity curve and the x-axis is the total distance traveled. And that's sort of the big conclusion here, maybe somewhat of a surprise, but that's the goal of all of this. The area between the velocity curve and the x-axis is the distance traveled. And in fact, that's what's written there as number 8. Here's the big conclusion. If we have a graph of velocity, the total distance traveled is the area under the graph. Fantastic. Okay, number 9, pause and read all of that if you haven't done so yet. Here we go. All right, so we're trying to calculate the distance, how far the car has traveled by finding high and low estimates. So everything's the same as before. The idea here, I'm not going to do this whole one out, but again, this first, we're doing, how many intervals are we doing here? 10-second intervals. Okay, so just use the dots that we have. Okay, so in this first 10-second period, we have a low velocity of maybe 35 and a high velocity of 50, and you can read them exactly from the table. And so if I wanted to estimate an underestimate in that first half hour, I would say, okay, let's just pretend this driver was going 35 miles an hour constantly for that first, I said half hour, I meant 10 seconds. And if I want to over an estimate, I would say, okay, well, let's suppose the driver was constantly going 50 miles an hour for that first 10-second period. But saying miles an hour, I'm not even sure. Feet per second. Missed on both counts. Same deal as with the zombies. You're just going to draw however many, I guess six rectangles here for a low estimate and 6 for a high. But I do want to point out that you should be able to do this without the graph, using only the table. The graph is here to kind of connect to what we just did with the zombies, but the fact is all you need are the numbers in the table. And I'd like you to be able to do this just with the numbers in the table. So try it with just the numbers in the table. I will write the calculation down in a second, so pause here, try with just the table, and then come on back. Okay, so for back, I'm going to go ahead and go to the space at the bottom and use the numbers in the table. All right, so our low estimate, distance traveled equals, okay, in the first 10-second period, we're going to pick the lower of the two speeds. We had 35 and we have 50. We're trying to do a low estimate, so we pick 35 times, this is velocity times time, 10 seconds in this case. That estimates the distance traveled in the first 10 seconds. It underestimates it. Okay, between 10 and 20 seconds, we pick the lower number of 50 and 61. That's 50. That's the velocity times time, 10 seconds. Plus, in the next interval, lower one between 61 and 69 is 61. times 10 seconds, plus between 69 and 76, we pick the lower one, plus between 76 and 84, we pick the lower one. Don't forget to multiply each of these by 10. And then between 84 and 90, we pick the lower one. And notice that the 90 never gets picked. Too bad for it. Okay, so that's our low estimate. And then the high estimate. In the first 10-second interval, your choices are 35 and 50. We're picking the higher one. Let's assume 50 feet per second times 10 seconds. Plus, and then between 50 and 61, we pick the higher one, etc. In both cases, we're doing 6 products and then adding them up. Notice that we pointed out in the low estimate, the 90 didn't get represented anywhere, and in the high estimate, it's the 35, the first number there that doesn't come into play. And so you just do the arithmetic, and I'm going to read off the answer key here. So this first one is 3,750. It was feet per second times seconds, so that's feet. And then the high estimate is 4,300. And so the best that we can do, we use the information that we had. The best you can do is maybe guess that the actual distance is the average of these two numbers. Again, there's no way to know for sure, and almost certainly that's not right, but it's the best thing we can do with the limited information we have. The graph up above has, curves connecting these points, assuming that, like the points are connected by very smooth, simple curves or even straight lines, but we don't know anything about that. All we have is the information in the table. So 4,025 feet is our best guess.